What if the laws of physics aren't laws at all, but lines of code, not metaphorical code, not the universe is like a computer poetry? Actual computation. Running, right now. And what you call reality is just what it feels like from inside the program. If that sounds impossible, try this. You've never touched the past. You've never held the future. You only ever experience a thin, updating slice called now. Like a screen refreshing. Like a simulation stepping forward frame by frame. And then the question gets darker. If reality is computation, who or what is doing the computing? Start with something you already accept. The universe is strangely mathematical, not just in a we can measure it way, in a the world behaves as if it follows precise rules way. Light moves at a constant speed in a vacuum. Electrons are identical everywhere, every time. Quantum fields obey equations that predict experiments to ridiculous precision. You can write down a few symbols on paper, and a particle in a lab will obey them like it has no choice. That's weird. Because in everyday life, rules are usually local. A traffic law exists because people enforce it. A game rule exists because the console enforces it. But the rules of physics don't seem to be enforced by anyone. They just happen, universally, automatically, with no exceptions ever observed. And then there's the discreteness hiding inside the smoothness. Matter comes in quanta. Energy is quantized. Angular momentum is quantized. The universe lets you turn the dial, but only in clicks, not a continuous slide. Even information has a physical flavor. Black holes, according to ideas from Jacob Bekenstein and Stephen Hawking, have entropy proportional to their surface area, hinting that reality might store information in a surprisingly pixel-like way, on boundaries. It's tempting to look at that and think, this is how computation works. Digital, chunked, countable. Then your attention goes to something else, limits. There's a maximum speed for causality, a maximum density before you get a black hole, a quantum limit to how precisely you can know pairs of properties, a thermodynamic rule that says you can't get information for free, erasing a bit costs energy, as Rolf Landauer argued. Even if you've never heard the name, you've felt the idea. Memory has a price. In a video game, limits are everywhere. Maximum frame rate, maximum render distance, maximum precision. Not because the world is stingy, but because computation is. So you begin building a hypothesis in your head. Maybe the universe has a kind of processing budget. Maybe physical law is what you get when reality must update consistently, everywhere, without crashing. Maybe the constants are not wholly numbers but settings, parameters that stabilize the run. And the deeper you go, the more coincidences start to look like clues. Quantum mechanics doesn't give you one certain outcome, it gives you probabilities, a spread of possible results until measurement happens. And what is measurement, really? It's interaction, entanglement, information becoming shared. That starts to sound less like mystical randomness and more like a system that doesn't commit to a full detailed state until it has to. Like procedural generation, like compressing the world until the player looks at it. Careful, that's an interpretation, not a proven mechanism. But the resemblance is there, and it's hard to unsee once it's pointed out. Then there's spacetime itself. In general relativity, gravity isn't a force in the old sense. It's geometry. Mass and energy tell spacetime how to curve. Curved spacetime tells matter how to move. It's elegant, but also suspiciously engine-like. A set of update rules linking the distribution of stuff to the structure it moves through. And that structure behaves like it has a resolution limit. People debate whether spacetime is ultimately continuous or discrete, but many approaches to quantum gravity suggest that at the Planck scale, the concept of smooth space may break down. If that's true, you don't have an infinite canvas. You have a grid so fine you've never noticed it. Now the implications start to swell. If reality is computation, then physics is software. Chemistry is software running on physics. Biology is software running on chemistry. Your brain is software running on biology. And you are the part of the computation that experiences itself. At this point, you might wonder if there's any way to test a claim like this, because if it's just a vibe, it's nothing. But people have tried to pin it down to consequences. One famous attempt comes from the philosopher Nick Bostrom. In 2003, he published an argument about simulation. If civilizations can reach a point where they run many ancestor simulations, then statistically, you might be more likely to be in one of those simulations than in the original base reality. It's not proof. It's a probability argument that depends on assumptions you may reject, but it did something important. It turned simulation from a sci-fi plot into a question with logic. Physicists have also played with the idea in narrower ways. John Archibald Wheeler talked about it from bit, suggesting that information might be fundamental, and physical reality could arise from yes-no questions at the deepest level. Seth Lloyd has described the universe as a quantum computer in the sense that physical processes can be viewed as information processing. Again, that doesn't mean there's a literal laptop outside spacetime. It's a framing, but it's a provocative one. And then you hear about attempts to detect pixelation in the universe. Some researchers have speculated that if spacetime were a lattice, extremely high-energy cosmic rays might show directional artifacts. Others have looked for tiny violations of Lorentz invariance, the symmetry underlying special relativity, because a discrete grid might introduce preferred directions. So far, experiments have not found clear evidence for such violations at accessible scales. That's not a win for the hypothesis, but it doesn't kill it either. A clever simulation could hide its grid, or the computation could be quantum and not a simple lattice at all. Your investigation spreads into stranger territory. Emergence. Simple rules can produce complex worlds. Cellular automata, like Conway's Game of Life, show how tiny local update rules can generate patterns that seem alive. Stephen Wolfram has argued for decades that simple computational rules might underlie physical law, and that what looks like randomness could be computational irreducibility, meaning you can't shortcut the result, you have to run it to see what happens. That idea is unsettling, because it suggests a universe where prediction has a hard ceiling, not just a practical one. Not because you're too dumb, but because the universe can't be compressed into a neat formula any further than it already is. And now you're at maximum suspense. The facts line up like hints in a mystery novel. Mathematics fits reality too well. Nature uses quanta. Information seems physical. Limits look like compute limits. Complexity emerges from simple rules. Some serious thinkers have entertained informational foundations. So are the laws of physics software. Here's where the story turns. Most physicists do not think reality is literally a computation, is an established scientific claim. And the biggest reason is simple. Physics already explains these facts without needing a simulator. Start with the mathematics is too perfect feeling. One mainstream view is that mathematics isn't a separate language imposed on reality. It's the distilled description of patterns you observe. You evolved to model the world. You invented tools that capture regularities. When the universe is consistent, math will fit, because that's what math is for. Then discreteness. Quantum mechanics is not pixels in a straightforward sense. It's a theory of how systems behave, and the quantization arises from boundary conditions, symmetries, and the structure of quantum states. Many quantum variables are discrete, but others are continuous. Quantum field theory still lives on continuous spacetime in its standard form, even if it has infinities you renormalize. The world isn't simply a digital grid. And probability. That the universe renders only when observed story is catchy, but it's not the consensus. The wave function doesn't necessarily represent ignorance due to lack of rendering. It's a mathematical object that predicts outcomes. Different interpretations of quantum mechanics, Copenhagen-like views, many worlds, Bohmian mechanics, cubism, disagree on what it means, but they largely agree on the same experimental predictions. The computational metaphor doesn't uniquely explain anything yet. Even the idea that information is fundamental doesn't require a programmer. Landauer's principle tells you erasing information has an energy cost, but that's because information is tied to physical states. It's not proof that physical states are made of information. It might be the other way around. Information is a way you describe physical states. And then there's a deeper problem. Computation, as you usually understand it, happens in time. It requires a sequence of steps. But time is part of what physics describes. So if the universe is a computation, what is the clock outside the universe that ticks it forward? If you answer, the computation is timeless, then computation starts to mean something far more abstract than software running on hardware. In other words, the more you try to make the hypothesis literal, the more slippery it gets. But the twist isn't that the simulation idea is silly. The twist is that software-like laws might be a mirror you're holding up to reality, not reality itself. Still, the mainstream explanation has its own holes. Physics has laws, yes, but why these laws? Why these constants? Why does the universe permit stable atoms, chemistry, stars, and minds? Some people invoke the anthropic principle. You observe a universe compatible with observers because otherwise you wouldn't be here. That's not an answer that satisfies everyone. It can feel like a shrug dressed as logic. And quantum theory plus gravity still don't fully fit together. We have no completed, experimentally verified theory of quantum gravity. We don't know what spacetime really is at the smallest scale. We don't know why measurement feels like a collapse or whether it truly is. We don't know if information is the bedrock or a shadow cast by deeper structure. So you end up with an uncomfortable intellectual standoff. The computational hypothesis can explain the vibe of limits and discreteness, but it struggles to produce unique, testable predictions that separate it from standard physics. It risks becoming a story pasted on top of equations you already had. The mainstream view can model reality astonishingly well, but it doesn't fully explain why the rules exist, why they're stable, or what the equations ultimately refer to. It can calculate, but it may not interpret to your satisfaction. And maybe that's the point. Maybe software is not a claim about a hidden server farm beyond the stars. Maybe it's a metaphor for something subtler, that the universe is structured in terms of relationships and transformations, and what you call matter is less like stuff and more like behavior. Like a pattern that persists because it is self-consistent. When you look at it that way, the question changes. It's no longer, are we in a simulation? It becomes, what does it mean for anything to be real if reality is a set of rules that never need a ruler? You can spend your whole life trying to find the hardware under the laws, or you can notice the stranger possibility that there is no under, that the laws are not a skin over reality, they are reality's grammar. And you, this brief thinking arrangement of atoms, are a sentence the universe can read back to itself. If the laws of physics are software, then you are not just living in the program. You are the part of the program that wonders who pressed run.